2. Derivatives. Section 3.4. The chain rule.
Lesson 1. The chain rule and the general power rule. Part 1.
In our last section on shortcut rules for the derivative, we're going to learn something called the chain rule. The chain rule turns out to be extremely important in all kinds of application problems. So it's very important to understand how to apply the chain rule correctly. And once you get the idea of how to apply the chain rule, it's easy to do. That's what we're going to do today, is try to learn to apply the chain rule. Let me review briefly what you've learned so far. You've learned how to find the derivatives of polynomials. You've learned how to find the derivatives of exponential functions and how to find the derivatives of trig functions, all using shortcut rules. And you've also learned how to find the derivative of a sum or difference of two functions, as long as you know the individual derivatives, and how to find the derivative of a product of two functions. So you've learned how to find the derivative of f plus g, if you can find the derivative of f and g separately, f minus g, f times g, the product of two functions using the product rule, and you've learned how to find the derivative of f divided by g, the quotient rule for derivatives. There's one way of combining functions that we have not yet discussed, and that is how to find the derivative of a composition of two functions. Remember, f circle g of x means the composition f composed with g of x, or in words we say f of g of x. G of x becomes the input into the function f. And that's what the chain rule applies to. So this is the one situation that we have not discussed yet. Well, before we get into a discussion of the chain rule and state what the rule is, I want us to think about this particular example. Suppose I ask you to find the derivative of 3x plus 2, that whole quantity squared. Well, we have a rule for the derivative of x to the n. That's what we refer to as the power rule for derivatives. But we don't have a rule when what's inside the parentheses is not just an x, but is a function of x, g of x, all raised to the n. So we don't have a rule for this. And that's the situation that I have here. It's not the derivative of x squared, it's the derivative of some function of x, which you could think of as g of x. It's a whole function of x squared. Now, is it impossible to do this derivative with the shortcuts that we've learned so far? No, it is not impossible. In fact, we could find the derivative of 3x plus 2 quantity squared, even though we don't have a rule for how to do the derivative of g of x raised to a power, simply by multiplying out what's inside before we find the derivative. So I could say, oh, well, that's not that bad. I'll find the derivative of, and I'll do 3x plus 2, that quantity times 3x plus 2. I have to FOIL it out, and I would end up with 9x squared plus, let's see, I guess it would be 12x plus 4. And then I get to use the sum rule and take the derivative term by term. So now I can go ahead and say, okay, well, that's going to be 9 times the derivative of x squared. That would be 9 times 2x, or 18x, plus the derivative of 12x would just be 12, and the derivative of a constant such as 4 is just 0. So I found the derivative, not a problem. Well, that's nice, but what if we look at the next example, and I ask you to find the derivative of the same inner function, 3x plus 2, that quantity, but now it's raised to the 100. We could, in principle, do it exactly the way we did this one. We could multiply 3x plus 2 times 3x plus 2, but how many of these factors would we have? We would actually have 100 of these factors multiplied together, And you could multiply the first two together by FOILing out. You'll get some trinomial, and then you could multiply by the next binomial, 3x plus 2, and so on. It could be done, but it would take a very, very long time. You'd probably make a mistake somewhere during that calculation anyways, and if you did, then you would get the wrong answer. What we would like is a faster way of doing this type of problem, and it will also apply to the first example that we looked at, and that faster way is called the chain rule. So let's go ahead and look at the chain rule and see what it says. It says, suppose I want to take the derivative of f of g of x. So it's the derivative of a composition of two functions. Notice it's not f of x times g of x, it is f of g of x. G of x is inside the f of x function. We've composed those two functions. What the chain rule says is that as long as the inner function g, I'll say if, g is differentiable, I'm going to abbreviate that, at x, and as long as f, I'll say and f is differentiable at the output of g at x, namely g of x, then the following chain rule holds. The derivative of the composition f of g of x is given by the following. We find the derivative of whatever the outer function is. We evaluate that at the inner function, g of x, and then we multiply whatever we get by another function, the derivative of our inner function, g prime of x. And I'll write out the words that I just said a little bit later, but let's go ahead and just keep the rule this way. The derivative of f of g of x is f prime evaluated at g of x times g prime of x. We're going to go back and look at this example that we did at first by multiplying out and then taking the derivative, and we're going to do it using the chain rule and at least check to be sure that we get the same answer that we did up here using rules that we know work. And by the way, I'm not going to prove the chain rule to you, but at the end of this section I will go ahead and give you a kind of an understanding or an explanation of what the chain rule is telling us, and hopefully it will give you some confidence that the rule that I'm giving you is correct. The appendix in your textbook does prove the chain rule, but it's rather long and difficult, so I'm going to skip that in the video. Okay. We're going to do this in kind of a long way first, and then once we get the hang of things, I'm going to show you how to do it in a quicker way. So the long way is to say, okay, here's my composite function, 3x plus 2, the whole thing raised to the second. And the first thing I want you to do is think about, if we think of this as a composition of two functions, so we want to think of what's inside here as some f of g of x. We're taking the derivative of. Let's try to identify what the inner function is and what the outer function is. And the inner function is usually easiest to pick out first. That's what's inside my parentheses here, so that is going to be my g of x. So g of x is 3x plus 2, and generally it's easier to find the inner function first. Now we ask ourselves, what would the outer function f of x have to be so that when I compose them and figure out f of g of x, I end up with 3x plus 2, that quantity squared. And we've done this process of pulling two functions apart. The outer function would have to be x squared. And if you're not sure, remember you can always write your outer function with empty parentheses. F of whatever I throw in is whatever I throw in squared. So if the thing that I throw in is g of x, you notice that g of x is what goes into the empty parentheses, and g of x is exactly what we want, 3x plus 2. And so f of g of x, if we call this g and call this function f, will give me the function that I'm asked to find the derivative of. So that checks, and we found the inner function and the outer function correctly. Well, let's look up here at the chain rule and see what things appear in the chain rule. One of the things that appears is f prime, and another thing that appears is g prime. Let's start by finding this factor g prime of x that appears on the right-hand side of the chain rule. G of x is 3x plus 2, so the derivative of that would just be 3. So we actually already know what this part of the chain rule is going to be. Now let's go over here and see some of the other things that appear in my chain rule. I need to find the derivative of my outer function. So let's go ahead and find f prime of x. F of x is x squared, so f prime of x would be 2x. Notice that if I wrote this with empty parentheses, f prime of whatever I plug in is 2 times whatever I plug in. I notice that what appears in the chain rule is not f prime of x, but rather it is f prime of g of x. So what I'm going to do is fill in these empty parentheses with g of x. So if I want f prime of g of x, that would be 2 times g of x. So it's 2 times my inner function. And what is my inner function? G of x is just this thing, 3x plus 2. So if I am asked to find the derivative of 3x plus 2, that quantity squared, I'm finding the derivative of some composite function. I'm just going to write the chain rule right above, in general, right above what I'm asked to do. I know according to the chain rule I'm supposed to get f prime evaluated at g of x times g prime of x. And let's see what that is for our function. F prime of g of x is what we found right here. F prime of g of x is 2 times 3x plus 2. And g prime of x we found right here. G prime we found is equal to 3. So all this stuff over here is like scratch work that we did on the side so that we could fill in f prime of g of x and g prime of x, the two factors that appear in the chain rule. Well, is this even the right answer? Remember, we got an answer up here of 18x plus 12. We know that's correct. Well, this, if I pull the 3 to the front, would be 6 times 3x plus 2, and that does give me 18x plus 12. That does give me the same answer I got by just multiplying out and taking the derivative term by term. Well, gosh, that looks like a lot of work to find this derivative that was really quite easy to multiply out. But remember, if we'd had a higher power here, we said it would be almost impossible to do the problem by multiplying out. In fact, let's go ahead and do this problem on the next page. We said we couldn't really do it by multiplying out except in theory because it would just take too darn long. Now before we go through and do that example, we'll do that right down here, I want to show you a quick way to do the problem that we just did. Notice that what we just did, I'll just go back to the last overhead for a moment, what we just did was an awful lot of work. We identified what f of x was, we identified what g of x was, we had to find g prime, we had to find f prime, then we had to find f prime not evaluated at x, but at g of x, and then we had to plug all those into the chain rule. It takes a long time that way. So let me show you the quick way, and it takes a little while to get used to this quick way, but I hope it will make sense to you now that we've done this the long way. So what we do when we want to do it the quick way is we think of the words that go along with the chain rule. The derivative of the composite function is supposed to be f prime of g of x times g prime of x. Well, what is that? That's the derivative of our outer function evaluated at the inner function g of x, and then we multiply by times the derivative of the inner function. Well, remember in our heads, and I'm going to write this down even though we're not going to do it this way when we do the quick way. in your mind, you're thinking, oh, I can see that the outer function is x squared because the inner function is what's inside these parentheses. This is our g of x. So we won't even write this stuff down that I'm writing in green, but if you think of the outer function as x squared, then think about taking the derivative of that outer function. I'm going to write the outer function with empty parentheses. Remember, the derivative of f of x is 2x, so if I wrote the derivative with empty parentheses, what would I be doing? I'd be pulling down the 2 and raising this now to the first power. Just like when I take the derivative of x squared, I pull down the 2, and it'll be 2 times x to the first power. But instead of actually writing all that out, we think about it in our heads as a function with empty parentheses, and we take the derivative of that outer function. So what we're going to start out with in the chain rule is doing the derivative of the outer function. I look at this outer function and say, well, it's something squared, so when I take the derivative of the outer, I pull down the 2, I now have whatever's inside my f prime raised to the first power. I've taken the derivative of the outer function. I'm supposed to evaluate that not at x, but at the inner function. And what is the inner function? It's just whatever's inside the parentheses here, namely 3x plus 2. I've taken the derivative of the outer and evaluated it at the original inner function, 3x plus 2. And the last part of the chain rule says I then multiply by, so it's times, the derivative of my inner function. Well, what's my inner function? It's exactly what's in the parentheses here, 3x plus 2. The derivative of 3x plus 2 would be 3. And so now I've done the same process that I did on the last page, but much quicker. I took the derivative of the outer. I don't evaluate that at x, I evaluate it at g of x, the original inner function. And then I simply multiply all of that by another factor that's the derivative of this inner function. And the rest of it's just simplifying like we did on the last page. We pull the 2 times 3 together, that's 6. I multiply by 3x plus 2 and get 18x plus 12. Or oftentimes we don't even multiply it all out. We just put the 2 times 3 together because that's easy. And we say 6 times 3x plus 2. Or if you want to, you can go one further step and multiply that out and get 18x plus 12. Well, let's try that on this function, 3x plus 2 to the 100. It really wasn't practical to do that by multiplying this out first and then taking the derivative term by term. Let's do it both the long way, and then down here we'll do it the quick way so that you can get used to both ways. And once we've done it the long way for one more example and then done it the quick way, I think you'll be on to the quick way and it'll be much faster to do it that way, and you won't have to do it the long way anymore. Okay, so now let's concentrate on this one. First of all, what's the inner function in this composite function? The inner function, it looks like, is exactly the same as our last example. So the inner function is still 3x plus 2. So g of x is that. If the inner function is 3x plus 2, what must the outer function be? What must f be so that f of g of x gives me quantity 3x plus 2 raised to the 100? Well, the outer function must be x raised to the 100. Okay, terrific. Now let's find all the other things that come up in the chain rule. We need the derivative of the outer function evaluated at the inner, and we need the derivative of the inner function. So we're going to fill these things in. G prime is exactly the same as our last example because g of x is the same. So the derivative of 3x plus 2 is 3. The derivative of x to the 100, well, I pull down the 100, I now have x to 1 lower power, the 99th. But remember that in the chain rule, we don't want f prime evaluated at x, we want f prime evaluated at the inner function, g of x. So I'm going to go ahead and write f prime with empty parentheses, and then we'll fill those empty parentheses in with a g of x. So f prime, of whatever I throw in is 100 times whatever I throw into it raised to the 99th power. So if I put g of x inside, then I have to put a g of x inside these empty parentheses. So I would end up with 100 times, well, what is g of x? G of x is our inner function, namely 3x plus 2, and all of that would be raised to the 99th power. So let's go ahead and write out then what the derivative of our function is. The derivative of our composite function, 3x plus 2 to the 100th power. Well, according to our rule up here, it's supposed to be f prime of g of x times g prime of x. So let's see what that is. F prime of g of x, well, that's what we figured out right here. You could think of this as all being a bunch of scratch work needed to find the derivative using the chain rule. So f prime of g of x is 100 times 3x plus 2 raised to the 99. And I have to multiply that by g prime of x, which we said is just 3. So I multiply all of that by 3. Let me pull the factor of 3 to the front. I would get 100 times 3 is 300 times 3x plus 2 to the 99. And we usually leave our answer this way because it's just too difficult to multiply out 3x plus 2 times itself 99 times. That's the whole reason we wanted to use the chain rule, was to avoid multiplying that binomial by itself a bunch of times. So the derivative is 300 times the quantity 3x plus 2, all raised to the 99. Well, again, that's a very long process to use in order to find the derivative using the chain rule. Let's try doing it the quick way, where we do a portion of this in our heads. So I'm going to take the derivative of 3x plus 2 to the 100 the quick way. And remember that in terms of our formula, we're doing the derivative of the outer evaluated at the inner times the derivative of the inner. So I go ahead and just think in my mind, the outer function is x to the 100. What's the derivative of the outer function? So in our heads we're thinking outer function f of whatever is whatever raised to the 100. What's the derivative of that outer function? Well, the derivative of whatever to the 100, we're going to pull down the 100 and we're going to raise our whatever we're evaluating our derivative at to the 99th power. That is this portion of the words, the derivative of the outer. 100 times whatever I'm going to plug in to the 99. But we're going to evaluate that at the inner. We're supposed to evaluate that at g of x. And what is g of x? It's whatever the inner function is, namely 3x plus 2. Now I'm going to multiply all of that by the derivative of the inner function. And the inner function is what's sitting right here. Derivative of 3x plus 2 is just 3. And you notice how quick this is. Now I just go ahead and say, okay, 100 times 3 is 300 times 3x plus 2, all raised to the 99. So that is the quick way to apply the chain rule, is by thinking, what's the outer function? We take its derivative and write it down with empty parentheses. We evaluate it at the inner function, so into those empty parentheses goes the original inner function. And then we simply multiply by derivative of the inner function. And so we look at whatever's inside and multiply by its derivative. Let's try one more together, and then I'll give you one to try yourself. Okay, we're going to look at this one. I'm asked to find the derivative of 2x cubed minus 7x plus 1, all raised to the 6th power. Again, you could multiply that trinomial by itself 6 times, get a whole bunch of terms, and take the derivative term by term, but it would be a very lengthy process. So instead, we're going to use the chain rule, and we're going to do it the quick way without bothering to write down specifically all of this information that we did on the first two examples. When I look at something like this, the very first thing I do is I try to identify what the inner function is. That's always the easiest thing to look for first. And so it looks to me as if the inner function, g of x, is what's inside the parentheses, 2x cubed minus 7x plus 1. That's my inner function. If that's my inner function, what does my outer function f have to be so that when I do f of g of x, I end up with all of this raised to the 6th? Well, my outer function must be f of x equals x to the 6th. But I'm just going to think of it in my mind as empty parentheses raised to the 6th power. Doing this the quick way, we will go ahead and say, well, I'm finding f prime, I'm going to put the derivative equals f prime of g of x times g prime of x. And so I'm going to go ahead and say, well, the first thing I want is the derivative of the outer. Remember, in our minds we're thinking, oh, the outer function is whatever to the 6th power. The derivative of that would be 6 times whatever I'm plugging into f prime, and raised now to one lower power, raised to the 5th power. So that's this portion of the words, the derivative of the outer, 6 times whatever I'm going to plug in to the 5th. We're supposed to evaluate that at the inner function. So I'm supposed to evaluate that at my original g of x. What is my original g of x? That's what I marked right here. It's 2x cubed minus 7x plus 1. Derivative of the outer evaluated at the original inner function g of x. Are we done at that point? Almost. But remember, we still have to multiply by derivative of the inner. So times the derivative of the inner function. Well, here's my inner function, 2x cubed minus 7x plus 1. Do I really have to write g of x equals that and g prime of x equals whatever the derivative is? No, I can just figure out that derivative. Derivative of the inner function is just the derivative of this polynomial, and I take the derivative term by term. Derivative of 2x cubed would be 6x squared minus derivative of 7x would just be 7, and derivative of the constant 1 would just be 0. So I'm multiplying by derivative of the inner, and that's just 6x squared minus 7. Usually it's traditional to pull the smaller factors to the front. So normally we would write 6 and then write times 6x squared minus 7. It's just a smaller factor because it's not raised to a big power like this. And then 2x cubed minus 7x plus 1 raised to the 5th. But that's just sort of convention. If you wrote the factors in their original order, that would be fine also. So that is the derivative of this function. And notice we didn't have to do all this scratch work that we did before. Derivative of the outer, evaluated at the original inner, times derivative of the inner. And then it's just algebra cleaning that up. Okay, let's go ahead and look at the next page. So on the next page, I'm asking you to find the derivative of another composite function. It's the derivative of sine of 4x cubed minus 2. Notice this is very different than the function sine x times the function 4x cubed minus 2. It's not sine of x times 4x cubed minus 2. That is not what we are given. 4x cubed minus 2 is inside the sine function. It's the argument inside the sine function. So this is a composite function with an outer function and an inner function. What I'd like you to do is to pause the video and see if you can figure out first what the inner function is, label that as g of x, then think in your mind what must the outer function be, and go ahead and find the derivative the quick way by finding derivative of your outer evaluated at your original inner, and then multiplying by derivative of the inner function. And think of those words that we wrote out on the previous page as you go through this. Then restart the video and we'll go through it together. Okay, let's try this together. So my inner function is what's inside the parentheses here. This is my g of x. G of x is 4x cubed minus 2. If that's my inner function, what must my outer function be? And again, this is something that you can just think in your head. You don't have to write it down. But my f of x, and I'm going to put f of whatever, has to be equal to sine of x. In other words, sine of whatever. So my outer function must be sine x. And if you compose sine of x with 4x cubed minus 2, if you do f of g of x, you will end up with sine of 4x cubed minus 2. So this is my outer function, and we're kind of just thinking this in our minds. Let's go ahead and see if we can do this derivative using the chain rule, but using the quick way. So, according to the chain rule, I'm supposed to start with the derivative of the outer function. Well, what is the derivative of sine x? The derivative of sine x, we know, is cosine x. So the derivative of the outer is cosine of x, but we're going to write that with empty parentheses. We're going to write it as cosine of whatever we decide to plug in. Well, what are we going to plug in? We're supposed to plug in the original inner function. So the chain rule says do the derivative of the outer. We did that, got cosine, but instead of evaluating at x, we're going to evaluate it at the inner function. So derivative of the outer, but evaluated at the inner. And what is the inner function? What is g of x? We said that's 4x cubed minus 2. So this first factor in the chain rule is derivative of the outer evaluated at the original inner. Are we done at that point? Not quite, because we have to multiply and add another factor here. So we have to multiply by the derivative of the inner function. So now I just say, oh, but my inner function is just this. I can find the derivative of 4x cubed minus 2. Derivative of 4x cubed is 12x squared. And derivative of negative 2 is the derivative of a constant, so that's just 0. So derivative of the outer is cosine, evaluated at the original inner function, 4x cubed minus 2, times the derivative of the inner function, 12x squared. For some weird reason, I'm not really sure why, oftentimes students misremember the chain rule and they put a plus sign here instead of a times sign. But that's not how the chain rule works. It's f prime of g of x times g prime of x. So I just wanted to mention that for some reason people, I don't know, confusing it with the product rule or something like that, but this is the chain rule and you multiply these two factors together, you do not add them. Now, just by convention, we usually pull these smaller kinds of factors and polynomial factors to the front of something that's a trig function or an exponential function. So normally we would write the answer as 12x squared, just reversing the order of these factors, times cosine of 4x cubed minus 2. So I'm hoping that when you tried the problem, this is the answer that you got. Or if you had trouble with it, you now understand how to do the chain rule on that kind of problem. Okay, well, let's go ahead and look at the second example on our page here. I'm asked to find the derivative of cosine 7x. And before we find the derivative, let's go ahead and rewrite this. This expression uses that shorthand notation that is exclusively used for trig functions, where the exponent is written between the cos and the x. In order to decide what the inner and outer function is, it's much easier to rewrite this without that shorthand notation. So remember that cosine 7x really means we're doing cosine of x, that function, all raised to the 7th power. And now it's a little bit clearer what the inner and the outer function are. Why don't you pause the video and give this one a try. Try to do it the short, quick way that we talked about, and write down as much as you need, but try this yourself, and then we'll go ahead and go through it together. Okay, so what's my inner function in this case? My inner function is what's inside the parentheses, namely cosine x. So my g of x in this case is cosine x. Now I have to think, what would my outer function have to be? What would f of x have to be? So that when I compose f of g of x, I end up with cosine of x all raised to the 7th power. And the only function that will work is x to the 7th power. Then f of g of x would be, well, let me write it with empty parentheses, f of whatever I plug in is whatever I plug in to the 7th. So f of g of x would be g of x to the 7th power, and g of x is just cosine x, so I would get cosine x to the 7th. Again, I think of this just in my mind, but at first, as you do the first few homework exercises, it's probably a good idea to write as much down as you need to, and then very quickly you'll see that you don't need to write any of this down. Okay, let's go ahead and try to take the derivative now. I'm going to write the pattern for the chain rule right above. I think that also is helpful. And then again later, if you don't need to, you can drop doing that. But we know that by the chain rule that we're going to do the derivative of the outer evaluated at the inner times the derivative of the inner. So we start with the derivative of the outer function. Well, if I took the derivative of f of x equals x to the 7th, I would get 7x to the 6th. We like to think of that just with empty parentheses. The derivative of the outer is going to be, well, derivative of x to the 7th is 7x to the 6th. But if I write that with empty parentheses, it would be 7 times whatever I'm plugging into my derivative raised to the 6th power. So when I take the derivative of this outer function, I'll draw a little arrow here, I pull down the 7, and it's going to be whatever I plug into the derivative of my outer function, all raised to the 6th power. Well, what am I plugging in? I'm supposed to plug in the original inner function, and g of x was just cosine x. So the thing that goes inside here is cosine x. So the first part of the chain rule is going to be derivative of the outer. I take the derivative of whatever to the 7th, so I pull down the 7, all of that to the 6th, evaluated at the inner function, and the inner function is cosine x. Now remember that there is another factor in the chain rule. I'm supposed to multiply all of this by g prime of x, that's the derivative of the inner function, and the derivative of cosine x is just a negative sine x. So I'm going to multiply that by minus sine x. So derivative of the outer evaluated at the inner times the derivative of the inner function. Well, let's go ahead and collect all the factors to the front that I can. I have a 7 times a negative 1, if you want to think of it that way, so it's minus 7. And at the end, we usually revert back to the shorthand notation, so I'm going to say minus 7. I have cosine x to the 6th. In the shorthand notation would be cosine 6x, means exactly the same as cosine of x to the 6th times sine x. Or if you want to, you could rewrite it with the sine x first. Either way is okay. Sine x times cosine 6x. So either of those would be an acceptable form for your final answer. And generally we tend to put the shorter factors or smaller factors first, and so probably people would write it in this second form. Okay, I want us to look at the next example, and the next example is also going to require a little bit of rewriting before we take the derivative. The problem is that although I have some inner function, namely 3x squared minus 5x plus 2 raised to the 2nd, it's down in the denominator of a fractional expression. Now, I could go ahead and try to use two rules. I could try to use the chain rule in conjunction with the quotient rule, because I have one thing, namely the function 1, divided by a function that's a composition of two functions, 3x squared minus 5x plus 2 raised to the second. So I could use the quotient rule and the chain rule together, but it turns out to be much easier to try to rewrite this expression first and avoid having to use the quotient rule. So is there a way to rewrite this expression so that it isn't a fraction? Well, yes, there is. I'm going to write the d by dx again because we're just rewriting. We're not taking the derivative yet. And how can I rewrite this? I could use a negative exponent. So I could go ahead and say this is the same as 3x squared minus 5x plus 2. But now I would raise not to the positive 2, but to the negative 2. And that, I think, will actually be slightly easier than trying to invoke two rules, the quotient rule plus the chain rule, to find the derivative. And we usually like to avoid the quotient rule anyways because, as you know, it gives you a rather complicated expression. So all I've done so far is to rewrite this by using a negative exponent, and that gets it away from being a fractional expression, just being some function raised to the negative 2. Great, so now I should be able to go ahead and try to apply the chain rule to this example. If you want to, pause the video, give it a try yourself. Just remember that at the end, we always like to write our final answer with only positive exponents. So we'll work with the negative exponents as we go through the problem, but at the very end, any exponents that are negative, we will rewrite with an equivalent but positive exponent. Okay, so let's go ahead and give this a try together. We need to identify what our inner function is first, and I can see that what's inside the parentheses here is 3x squared minus 5x plus 2. That is going to be my g of x. Now I have to think in my mind, what would f have to be so that when I compose f of g of x, I would end up getting this expression that I'm trying to find the derivative of. And the only function that will work is x raised to the negative 2. So in our minds, we're going to think of this with empty parentheses. It's f of whatever I plug in equals whatever I plug into the negative 2. And yeah, just as a check in my head, I can see that if I go ahead and plug g of x into these empty parentheses, I would have g of x to the negative 2, and g of x is exactly the polynomial that I want to be inside these parentheses. So f of g of x, if I label f and g this way, does give me the function that I'm asked to find the derivative of. All right, let's go ahead and write down, as we usually do, the pattern for the chain rule. And so I'm supposed to do the derivative of the outer evaluated at the inner times the derivative of the inner function. So let's do the derivative of the outer function. When I take the derivative of x to the negative 2, remember I will get a negative 2x to 1 lower power to the negative 3. So with empty parentheses, the derivative of the outer is going to be negative 2. It's going to be at whatever place I evaluate it at, all raised to the negative 3. So what I do is I just look at this outer function, think, something to the negative 2. I pull down the negative 2, and I do that something all to 1 lower power, so that would be to the negative 3. Well, that's the derivative of the outer function. Now I want to evaluate it at my inner function. And what is my g of x in this case? It's just this polynomial, 3x squared minus 5x plus 2. So that's the derivative of the outer evaluated at the inner. Now I have to multiply that by the derivative of the inner function. The derivative of 3x squared minus 5x plus 2, that's easy. Or sometimes you can look right here and say, I'm taking the derivative of whatever is inside here. And I do need parentheses in this case since there's going to be more than one non-zero term. So I end up with 6x, derivative of 3x squared would be 6x minus 5, and the derivative of 2 would just be 0. So that is my derivative, and now it's just a matter of kind of cleaning it up using algebra. Again, usually we pull the short factors to the front, so I would write that this way. I would write it as, let's see, negative 2 times 6x minus 5. And then I'm going to multiply that by what's left, 3x squared minus 5x plus 2, all raised to the negative 3. Hope you can see that negative sign right there. Now, the only problem with the answer that I have is that I do have a negative exponent here. And in our final answer, we always like to rewrite things using only positive exponents. So remember that I can rewrite that expression raised to the negative 3 as the same thing but a fraction, 1 over that whole expression, 3x squared minus 5x plus 2, but now raised to the positive 3 when I move it into the denominator. Well, again, we don't usually write it as two separate factors like this. Remember, all of this could be thought of as being over 1, so I can multiply all the tops together and the bottoms and get a single fraction. So I would write my final answer this way as negative 2 times 6x minus 5 times 1, so that is just itself. And down here, 1 times all of this stuff is just all of this stuff, 3x squared minus 5x plus 2, all raised to the third power. So I would probably leave my final answer this way. Sometimes the numerator will get multiplied out if it's easy to do so. So you could also write this as negative 12x plus 10 in the numerator, all divided by this stuff to the third power. That would be fine as well. Okay, let's go ahead and look at a couple more examples, and then we're going to talk about a special case of the chain rule. So let's look at the next page. And what does the next page have for us? Well, we have another example at the top where we are asked to find the derivative of something that involves the exponential function, the natural exponential function with base e. So we're asked to find the derivative of e raised to, and notice all of this is in the exponent, negative x to the fourth plus 7x cubed minus 2x. Well, in one like this, I like to put parentheses around the function that's in the exponent. The reason being that it's a little bit easier to see what the inner and the outer function are, and we need to know that in order to apply the chain rule. So what's the inner function in this case, and what is the outer function? The inner function in this case is what I have in these purple parentheses. It's whatever is up in the exponent in this case. So the inner function, my g in this case, is actually going to be this whole thing. It's going to be negative x to the fourth plus 7x cubed minus 2x. So that is my g of x for this particular problem. Well, if that's the inner function, we have to think in our minds, what would the outer function have to be so that I end up with e to the minus x to the fourth plus 7x cubed minus 2x when I compose those two functions. So let's go ahead and see if we can think about that. My outer function, the thing that this g of x is inside of, is the e to the x function. Think of it with empty parentheses if you want to. It's really e to whatever I plug in. So f of whatever I plug into this function is e to whatever I plug in. And you can see that if what I plug in here is g of x, then what goes up in the exponent here would be g of x. And g of x is exactly this function, minus x to the fourth plus 7x cubed minus 2x. So that's what would go in here. So it's always good to sort of double check in your mind that you really identified your inner function and your outer function correctly by going back and composing them and thinking in your mind, well, what would f of g of x be? It would be e to the g of x, which would be e to this polynomial. But that looks correct. So now let me go ahead and write down the pattern above for what the chain rule says the derivative is going to be. And again, it's the derivative of the outer function evaluated at the inner times derivative of the inner function. Well, let's go ahead and think about the derivative of the outer function. Remember, in this case, the outer function is f of x equals e to the x. Well, we've already learned what the derivative of that function is. Remember that e to the x is a very special function. It's its own derivative. So when we take the derivative of e to the x, we get e to the x. I'm going to actually write that in a little cloud over here just because it's such an unusual function. When I take the derivative of e to the x, I get the same function back again. It's its own derivative. And so if I were to think of that with empty parentheses, f prime of whatever is also equal to e to the whatever. So when I take the derivative of this outer function, what do I end up getting? I get exactly the same function back again. So I'm going to get e raised to the whatever. So derivative of the outer, in this case, it's its own derivative, so we get e to the whatever. I'm supposed to evaluate that at the inner function. Well, what is the inner function? The inner function, g of x, we said, is minus x to the fourth plus 7x cubed. Oops, looks like I don't have quite enough room there, so we'll use a little eraser transformation. Move my parentheses over. So inner function is minus x to the fourth plus 7x cubed minus 2x. So far we've done the derivative of the outer, it was its own derivative, evaluated at the inner function. And now the chain rule just says take that and multiply by derivative of your inner function. So we're doing the derivative of this inner function. Well, let me put parentheses there because I can see that I'm going to have more than one non-zero term. I'm taking the derivative of negative x to the fourth, that would be minus 4x cubed, plus the derivative of 7x cubed, that would be plus 21x squared, and then minus the derivative of 2x, that would be a minus 2. And now we're essentially done, except maybe cleaning it up and making it look a little bit nicer. But I've done derivative of the outer, evaluated at the inner, times derivative of the inner. Again, usually polynomial factors are written first, and exponential or trig factors are written second. So I would end up with minus 4x cubed plus 21x squared minus 2 times this other factor, e to the negative x to the fourth plus 7x cubed minus 2x. And you can either put parentheses on that exponent here, or you can leave them off. Either way is okay. Generally, in a textbook or something like that where it's really clear that all of this is in the exponent, they often won't write the parentheses there. But when we're doing it by hand, because we're a little bit sloppy writing things by hand, we sometimes put the parentheses in there to make it really clear that all of that is in the exponent of the e to the x function. Okay, I want you to go ahead and try the next example yourself. It also involves an e to the x function. So see if you can identify what the inner function is, what the outer function is, then go ahead and apply the chain rule to find the derivative of that expression. And once you've unpaused the tape, we'll go through it together. Okay, well, I always like to figure out what my inner function is first, and I can see that what's inside these parentheses is x to the fifth plus e to the x. So that is my g of x. And in my mind then I'm thinking, well, what must the outer function be so that f of g of x will end up being this thing to the fourth power? And my outer function, I can see, has got to be x to the fourth. So that means that f of whatever I throw into this function would be whatever I throw into the fourth. So if I do f of g of x, I would have g of x to the fourth, and that would be the correct composite function because g of x is just x to the fifth plus e to the x, and all of that would be raised to the fourth power. So that looks great. So let's go ahead and see if we can try to find the derivative of this expression. Again, I will try to write rule right above f prime of g of x times g prime of x. That is my chain rule. So the first thing I'm supposed to do is find derivative of the outer function. Well, my outer function is the x to the fourth function, or if you think of it with empty parentheses, you can think of whatever to the fourth power. When we take the derivative of x to the fourth, we get 4x cubed. I'm just going to go ahead and write that derivative with empty parentheses. So I pull down the 4 from my outer function, and I now have all of the stuff that I'm going to plug in the inside raised to the third power. And we say that we've taken the derivative of the outer function. I'm supposed to evaluate that at g of x, at the inner function, and we said g of x is exactly this function, x to the fifth plus e to the x. So that is the derivative of the outer evaluated at the inner function. Now I just have to remember the other factor in the chain rule. I'm supposed to multiply by the derivative of the inner function. I usually look right here and say, okay, here's my inner function. I want to multiply by its derivative. And what is its derivative? Well, I take the derivative of x to the fifth. I would get 5x to the fourth plus the derivative of e to the x. But what's the derivative of e to the x? It's its own derivative, so it is itself, e to the x. So this would be derivative of the outer evaluated at the inner times derivative of the inner function. Again, we usually pull the kind of shorter factors or the ones that aren't raised to an exponent to the front. So normally we would write this in the following way and just reverse the order of some of these factors. I'd put the 4 and then the 5x to the fourth plus e to the x, and then multiply that by the sort of bigger factor, the one that's to the bigger power, x to the fifth plus e to the x, all raised to the third power. And so you would usually see the answer